Hi, welcome to Nuclear Energy. This is 3.4. This video is going to cover nuclear energy, uranium, a history, some dangers, the process of fission, what a fission chain reaction is, power plants, and fusion. So, nuclear energy. Nuclear power is the only major source of energy that is not ultimately dependent on the sun. Uranium is a non-renewable fuel used by nuclear power plants. It is radioactive and a naturally occurring element. It is found in an ore called pitchblende or in uraninite ore. Most of the uranium that we use in the United States is imported from Australia and Canada. Some brief history. Uranium was originally discovered by Martin Klaproth in 1789. During the 1800s, though, people didn't understand the hazards of it and actually used uranium to make yellow glasses and paint. In 1896, Marie Curie noticed that the effects of uranium and named them radioactivity. In 1934, Enrico Fermi demonstrated that neutrons could actually split many kinds of atoms. The first self-sustaining nuclear reaction occurred at the University of Chicago in 1942. Electric power was first produced from nuclear energy at the Breeder reactor in Idaho in 1951. And in 1954, the USS Nautilus was the first nuclear-powered submarine to be launched. The first town powered by nuclear power was Arco, Idaho in 1955. And in 1986, Chernobyl was the worst nuclear-powered disaster of all time. It is in the Ukraine, and the city of Chernobyl is still uninhabitable today. So there are obviously some dangers of radioactivity and nuclear energy. The waste produced by nuclear power plants is radioactive, and the particles, those radioactive particles that they produce, are harmful to all living things. There is no good way to get rid of nuclear waste products. So it has to be stored for thousands of years. There are some mountains that are completely dedicated to storing nuclear waste. Energy can be obtained in two ways. Fission, the splitting of atoms. You get the energy if the nucleus is big and it breaks into smaller ones that are more stable. This is what we do in nuclear reactors. And then we have fusion. Fusion is the joining of atoms together. This we get the energy if the nuclei are small, then the larger one that they make is more stable. This is how the sun works. So nuclear fission is a process of splitting atoms into two. Fission means to divide. Fission is the splitting of atoms. These are usually very large so that they are not as stable. And a fission chain has three general steps. The first is the initiation. Second is propagation. That's why it's a chain reaction. And then third is termination. Nuclear fission, a very heavy nucleus splits into more stable nuclei of intermediate mass. The mass of the products is less than the mass of reactants, and that missing mass, because we do have the law of conservation of mass, that missing mass is converted to energy. This diagram shows a fission reaction where a neutron hits a uranium-235 atom and it breaks it into krypton-92 and barium-141 plus 3 additional neutrons and a lot of energy. Same example, just slightly different. A chain reaction is an ongoing series of these fission reactions. Billions of reactions occur every single second in a chain reaction. On Earth, nuclear fission reactions take place in nuclear reactors, which use controlled chain reactions to generate electricity. Remember that a chain reaction occurs when a critical mass of uranium undergoes fission, releasing a large amount of heat and energy, and that produces a very small atomic explosion. Here's a video explanation.
We use electricity to power every aspect of our lives. Simple stuff like making a cup of tea or powering our tablets and phones. We are on a journey to find out where some of this electricity comes from. We're inside a nuclear reactor, and if you look below you, you'll see we're travelling downwards, towards the reactor core. This system has just been refueled. It is powered by fuel rods that contain uranium, which is a natural element that is mined from deep in the ground. We keep it here, inside these metal rods. Let's take a look inside. The system is about to be switched back on. To see how uranium makes energy, we'll need to get smaller though. Now we're shrinking to an atomic level. Here, right in front of you, there's rows and rows of uranium pellets. In total, there are over 2 million fuel pellets in the whole reactor. And it's inside these pellets, each only a centimetre tall, that nuclear fission happens. Let's get even closer. At this scale, we can see actual atoms and neutrons. Neutrons are the particles that help us unlock all that energy from the nucleus. But they move fast, so first we need to slow one down. And to do that, we simply use water. Let's follow this one and see where it leads us. Pay close attention. Firing this neutron into the nucleus of the atom causes the nucleus to split in two. This is the fission we mentioned earlier. And as the nucleus splits, it releases its own neutrons. Some of these newly released neutrons, slowed by the water, hit other atoms, causing more fission. And so the chain reaction begins. In our reactor, there are an incredible 5 million fissions per pellet per second. Look around you, and you'll see them happening everywhere. Each time a uranium nucleus splits, it releases its awesome energy. This energy heats the fuel pellets and in turn the water in the reactor to more than 300 degrees Celsius. The powerful chain reaction has heated the water in the reactor core, and this heated high-pressure water now travels through pipes out of the reactor vessel at 35 miles per hour. It all sounds very dramatic, but understanding the physics means we know how to regulate the chain reaction. In the space beyond the pipe, the heat from that water turns more water into steam. This steam is what drives the turbines. All of that power just to make a turbine spin. It's really quite a simple system. These steam-driven turbines generate more than 1,000 megawatts of electricity. That's roughly enough to power all of the houses in Greater Manchester. All of the steam leaving the turbine is condensed back into water and pumped back round to the steam generators to be turned back into steam again. So, here we are, back in the main reactor where we started. You see, the simplicity of this system makes nuclear power incredibly effective. As you've seen, with nuclear, a little goes a very long way.
So let's take a closer look at those nuclear power plants. Inside a nuclear power plant, the fission is used to produce energy. The control rods in the reactor absorb the neutrons to slow and control the chain reactions of fission. In this diagram of a nuclear power plant, A is the containment structure, the building that the actual reaction takes place in. B are the control rods that help to control the chain reaction. C is the reactor itself. D is the steam generator. E is the steam line. F are pumps. that pump the water into and out of wherever they need to go. G is the generator itself, because remember, the steam comes and it turns the turbine, and that goes into the generator, therefore producing electricity. L is that transformer. I is the first cooling water condenser, and J is actually a cooling tower. And in that smoke, it's not really smoke, it is literally a cloud. It's carbon dioxide and water that is being released from the cooling tower. K are the actual fuel rods. That's where the uranium actually is. You're going to have to put one of these together later. Nuclear fission is, of course, the combining of two nuclei with low masses to form one nucleus of larger mass. Nuclear fusion reactions are also called thermonuclear reactions. Fusion reactions exist in stars, and our sun is a perfect example of a fusion reaction. It's almost impossible to create fusion reactions here on Earth since they have to have really high temperatures in order to make the atoms fuse together. Light mass nuclei combine to form heavier, more stable nucleus, more energetic than fission reactions. So here we have hydrogen 2 plus hydrogen 2 makes helium 4 and a lot of energy. That's the reaction that takes place in our sun. Scientists are experimenting with nuclear fusion reactions here on Earth. They do produce less waste, and the materials are actually easier to obtain. The difficulty they're having in producing this is finding enough of the deuterium, H2, and tritium, H3. Thanks.